All right, introduction to mass spectrometry. Now, it's not spectroscopy because we're not using the electromagnetic spectrum. It's mass spectrometry because we're trying to figure out the molar mass. And so we're going to be using a different type of energy. First thing that we want to think about in a mass spec is a compound is actually vaporized and then ionized, and then it undergoes fragmentation. We are destroying our compound. So it's really important about mass spec is that we actually will be taking the compound, making it break apart in the fragmentation process and trying to identify the fragments and any fragmentation pattern that we may see. Again, it's the same idea as solving a puzzle, but it's really that vaporization, ionization, and then fragmentation pattern that we will be looking for. Masses of the ions, when that compound fragments, it will be ionized, or parts of it will be ionized, and the ions are detected and graphed in the mass spec. So, most common method of ionizing molecules is by electron impact, EI, mass spec. The sample is literally bombarded with a lot of electrons, and that usually causes an electron from our actual compound to be ejected from the molecule, right? So this guy goes whee off on a vacation to Walt Disney World. Now the compound is a radical cation, and this is where our molecule will be detected. It has to be ionized, and when that electron gets lost, we are losing one electron, right? And that one electron leaves behind a radical cation. The radical cation that is formed can then fragment and start to decompose. The mass of the radical cation is known as the parent compound, right? It's still the parent compound. Even though we've lost one electron, it's still the same thing. It's also called the molecular ion. Remember, one electron has a negligible mass. The mass of an electron is about 1,000 times smaller than protons and neutrons. And so their masses are not counted in the masses of compounds, right? We only count up protons and neutrons when we're actually doing a molar mass or molecular mass. So the molecular ion is this radical cation that first forms once we bombard it with electrons. And so we'll call that, or we'll abbreviate it, the M plus radical peak, right? That's the parent ion, the parent compound. It's the molar mass of our compound that we're trying to determine. And then it can fragment. And when it fragments, it forms a radical and a cation. So notice here the curved arrow, the fishhook arrow, one electron will go to one side of that molecule, right? And what forms is a radical and a carbocation. The ions are deflected by a magnetic field and their mass to charge ratio is detected. Now their charges will always be then +1, so it will be a mass that is detected. We are going to assume the mass to charge ratio is the molar mass. Neutrally charged fragments, radicals, are not detected, right? So we're really trying to figure out how is this molecule fragmenting so that we can start to identify different pieces of the molecule itself. It does help with structure. Mass spec does help identify structure, but really at the end of the day, what we truly want to use it for is the mass identity and the molecular formula identity of a compound. Now, the mass spectrum shows the relative abundance of each cation that was detected. So the higher the peak, the more that fragment was detected. And so the base peak is the tallest peak on a spectrum. There's the base peak. It sometimes can be the molecular ion peak, the parent ion. For methane here, it is, right? 16. 16 for the charge to mass ratio, 16 for the molecular mass. It doesn't always have to be the same. The tallest peak is called the base peak. The parent ion is the peak that is the actual molecular mass. We'll show a couple of examples where those are different. Now, to understand those fragmentation patterns that happen with methane, typically the thing that holds a carbocation better, or a plus charge better, is a carbocation. So what we can see with that spectrum is that the base peak, or the molecular ion, was seen in most abundance, right? MZ of 16. The next highest peak was 15, right? Let's go back to that. Next highest, right? What is this at 15? It must be the CH3 carbocation. One hydrogen got plucked off, right? Now, subsequent hydrogens could keep plucking off, right? Subsequent hydrogen radicals can fragment to give the lower charge mass to charge ratios as well, the 12, the 13, and the 14 that we saw. Now, where do we use mass spec? Well, if you've ever watched a crime scene show, I know those were super popular when I was in high school, and they hired a lot of scientists to talk about instrumentation, and mass spec was the easiest thing to say. Mass spec is a relatively sensitive analytical method. It's used in pharmaceutical drug discovery, drug design, metabolism, biotech uses it. I used it a lot when I worked as an environmental chemist for Southern California Edison back in the day. We used it for water quality testing. It is very good at identifying masses, right? That's pretty much what we do. I used it also in conjunction in research with other instrumentation, such as high performance liquid chromatography and gas chromatography. These types of techniques you will not usually see in our organic chemistry class. We just usually don't have time for them. They're very interesting. There is a gas chromatography section at the end, which I'll just briefly go through for interesting perspectives. But a mass spec, again, what we are going to be using it for is mass determination. And we will be looking at the fragmentation patterns a little bit. All right, analyzing that parent ion peak, right? So looking for the parent ion, again, it's going to be the one that is the actual base, the furthest peak to the right, the highest number here on the right-hand side. I'm going to zoom in. Here is our molecular ion peak, our parent ion. It is also, again, the base peak. It's the most prevalent fragment that came to be. This is benzene's mass spec. Benzene does not fragment easily. Again, we see a lot of fragments of one, which is the hydrogens falling off, right? We will talk about what is this peak, in just a minute. For most compounds, the parent ion peak is not the base peak, though. When we look at something else, for more easily fragmented structures, linear structures, those compounds like pentane here, the parent ion, the molecular ion peak right there, it's the highest one on the far right-hand side. The base peak is, again, the highest one out of everything. What that base peak is really good to look at is because that structure or that fragment should be stable as a carbocation. And so when we're looking at this, if we would count 40, 41, 42, 43, right? The parent is 72. The highest base peak is 43. So if we subtracted those, we're getting a difference of 29, change of 29. What's interesting and what we will hopefully develop by the end of this is the idea that what is that? Well, let's chop it off right there. A CH2, CH3 group has a mass of 29. Right? So we're going to start to see similarities, and there is a nice chart at the end of this lecture and in your textbook that will be very helpful for us to start to identify different chunks. What mass values are we looking at? Now, in analyzing the parent ion peak, Something that's very important is the mass to charge ratio of the parent ion will be the molecular mass or the molar mass of the compound. An odd massed molecular ion peak generally means that there's an odd number of nitrogen atoms, and an even mass of peak generally indicates that there is an absence of nitrogen or an even number of nitrogens present, right? So odd numbers, think about nitrogen. Even numbers, we can either go either way, no nitrogens or 2 nitrogen atoms. We will discuss how to come up with the molecular formula a little bit in class, but that's not something that I'm really here to assess. I really just want to be able to look at a mass spec and decipher a couple of things about it. All right, for methane, let's talk about that little peak that we've been seeing over here that I've been ignoring. And you're like, what is that? The M+1 peak, or the parent ion plus 1. This is our base peak and our parent ion, right? At 16 mass to charge ratio, grams per mole, right? What is that at 17? Well, if we remember, 1.1% of all carbon atoms are carbon-13. So we have here the identity of isotopes. Mass spec is actually one of the ways that we decipher and identify the abundance of isotopes in real life. So whenever we calculated from isotopic abundances, in general chemistry to find the isotopic mass or the average isotopic mass that we find on the periodic table, those are determined from mass spec data of the actual sample of pure atom itself. And so we see a tiny little peak, usually M+1 is what we call it. And that is primarily because we have a lot of carbon in our samples. This is organic chemistry, right? And carbon-13 is an isotope of carbon. That is in a 1.1% abundance, but that's why we see that tiny little peak. If the M+1 peak is a little bit larger, you might have different isotopes, different things in the solution. Notice here the value or the height is a little bit higher than that of the parent ion peak. Decane, right? C10. So the more carbons you have, the higher that M+1 peak will be, the taller it will be. All right. So the ratio of molecular ion to M+1 peak will be able to, will help you estimate how many carbons are in the molecule, right? M+2 peaks exist as well. Technically, they're not prevalent for carbons. They are prevalent for other heteroatoms, chlorines, bromines, things like that. Chlorine has 2 abundant isotopes, chlorine-35 and chlorine-37. And we see that those, the parent ion, the M, and the M+2 here exists with a little bit closer values, right? 75% to 25%, if you want to think about that. 1 to 3 ratio, right? 3 to 1. There, if we think about those, the height differences, right? So we can use the height differences, the relative abundance of our lines to start to identify heteroatoms in a compound. Again, matching things, right? That's what our main goal is for this. Bromine has 2 isotopes as well. So we'll see a molecular ion peak and an M+2 peak. Bromine exists as bromine-79 and bromine-81. More of a 50-50 ratio there, right? So we see that the molecular ion, the parent ion, there is the same height as the M+2. We still do see the M+1 and this little M+3 for the carbon-13 isotopes in each of those isotopes, right? Lots of isotopes on isotopes. Analyzing the fragments, big thing to start thinking about. Let's go back to that pentane structure that we saw. The parent ion was the full 72 charge to mass ratio. The base peak was 29, right? And so that base peak of 29 tells us that the typical fragment that we would see is 3 carbons for that carbocation and ethyl group popping off, an ethyl radical popping off. But we still did see the parent ion minus 15, right? That's what this tells us. M minus 15, 72 minus 15. And what is that? 57, right? So there was a peak at 57, which was that fragment. There was a peak at 43, which was 72 minus 29. And then we did again see a peak at 29 and there at 15. So what we're starting to see is that the mass spec is detecting the charged fragments, the positively charged fragments. And when we look at the spectrum, what we should be able to start to decipher is the tallest peaks in a group can help us understand what fragment popped off, what fragment was left over, things like that. Again, there's our parent ion right here at 72. We popped off a methyl group, right? And then we popped off the ethyl group, right? Those are what were subtracted, et cetera, et cetera. So we can start to build up the structure from there. Analyzing the fragments is what we're going to get to right now. This is the chart I was talking about earlier. This chart is extremely helpful. To be able to see the parent ion minus 15 means you lost a methyl radical. If you see a minus 29, you lost an ethyl radical, et cetera, et cetera. We won't be getting into the McLafferty rearrangement for ketones or aldehydes, not doing anything that complex. What I want to be able to look at mass spec for is identifying the parent ion, the base peak, and any fragmentation pattern that is simple here on these first few. All right. I know. Lost your electron? You got to keep an eye on those. Remember that the mass spec only identifies the ion, right? That's what the peaks are, the ions, not the radicals. The radicals are chopped off and eliminated and not detected. Only the ions are detected by mass spec. All right, lastly, this little bit is just the real life application. It's optional, not necessary for this class, but if you want to know about where mass spec is used in real life, technically what we usually use is high resolution mass spectrometry. And why we do that is because the mass can be measured within up to 4 decimal places. If we remember, 1 proton is not 1 AMU, it's 1.0073 AMUs, and 1 neutron is not 1 AMU, it's 1.0086. So we can see the difference that no decimal places versus 4 decimal places makes, right? And so looking at high resolution mass spec, the exact abundances, natural abundances and masses will be determined. And so looking at high res mass spec allows us to distinguish between compounds that have the same molecular weight. Because notice down here, cyclopentanone, this ketone versus cyclohexane. Both have the same 84 grams per mole AMU. But technically, because of the oxygens and hydrogens and carbon counts, they are slightly different masses, right? We would not be able to distinguish these two in a typical low-key mass spec. You would need a high resolution mass spec, right? So things that have 4 decimal places or more. And again, I kind of hinted towards this. You usually tie mass spec in with something else. You don't just pop a sample in mass spec. You can do that. That is okay. A lot of the crime shows have done that. Where you're like, I put it in major mass spec, or I put it in this and I found out it was this. And it's like, well, really, that's an oversimplification, right? Because it's Hollywood, it's television. In research, what you would want to do is you would have a sample of probably a couple of different things, and you would want to use some sort of separation technique, chromatography, prior to the mass spec. So yes, you still want your sample to be vaporized, ionized, and then fragmented, but you want your sample to be as separate as possible. And typically in research, we don't just have one compound in a sample. We have multiple compounds in a sample. So yes, mass spec is suited for identification, but it's not good for separating different components of a mixture. Things like a gas chromatography instrumentation can be used to separate mixtures. Essentially, this is just a big oven. It heats up your sample. It's really good with organic molecules because organic molecules are highly volatile. So you stick your sample right here, right? Whoop, and you push it along with some inert gas, something like argon or nitrogen or something that's not going to react with the sample itself. It just helps push it along. Gas chromatography, so that's the carrier is a gas, and you have this really long column, usually a few meters or so, 200 meters I've seen before, wound up in a nice little circular shape in this oven. It's heated to over 200 degrees Celsius so that we can vaporize, turn your sample into a gas. And as the sample pushes along this column, it separates big things and small things. That's what a gas chromatography instrument does. It separates by size, polarity, different types of things, depending on what your column is. And then one at a time, your sample can actually go into the mass spec. You have your electron beam, your ion source, right? And that's where you ionize. So you vaporize over here, then you ionize, and then you fragment in the ion sorting region. Now, GC gives you a chromatograph. Mass spec gives you the spectrum of the masses. So each peak in a chromatograph identifies a different compound, a different component, right? So when we're looking at this, we have 1, 2, 3, 4, 5 different components in our sample. Each one of these will have a mass spec to go with them because one at a time, they came out of the gas chromatogram and they went into the mass spec. And so the mass spec is able to decipher each individual component. It's a great technique for complex mixtures.